When we get down to the size of an atom, we've got so many different things happening. The uncertainty principle, we're going to have the de Broglie wavelength. All these things are going to make it very complicated and cumbersome to try to just use a simple definition or a simple word. We have to be a lot more specific when we talk about something like size. So atomic size, one way of looking at that is the volume inside which we have a 90% chance of finding the electron. Great, that's how we've defined it when we talked about orbitals, but that's going to be really challenging to use experimentally, right? So instead what we're going to do most of the time is we're going to be talking about the atomic bonding radius, or we can talk about a non-bonding atomic radius. Now notice the non-bonding atomic radius is going to be the size of the atom when it's all by itself. Bonding radius is going to be a little bit smaller. You can see that right here. Now to measure a bonding radius, what we do is we take a homogeneous molecule, so a homogeneous diatomic molecule, that's going to have two of the same atom, homogeneous in other words. We can take the distance between the two and divide it in half, and that will become our non-bonding atomic radius for each individual type of atom. So we'd have to do that over and over again. Now, if we were to do that for something like chlorine, we'd get the bond length to be 199 picometers. When you divide that by 2 to get the covalent bonding radius, you decide that it's going to be about 100 picometers for our chloride bond, for a chlorine atom, I should say. Now, if we then do the same thing for carbon and find carbon's distance to be 77, we're going to predict 77 plus 100 should be about 177 picometers apart. And that's actually not a bad estimate of what the actual carbon-chlorine bond length will be. So we often will use that, and it turns out you sometimes get a 1, sometimes even as much as a 5% error in that, but that's still pretty good for a very simplistic method. For more detailed sizes, that's when we get to go play with fun and supercomputing clusters and quantum mechanics.